It's a pleasure to have today's speaker, Eliot Quataert, for today's seminar. He's a professor at Princeton University, the Charles A. Young Professor. He's been there for a few years, and before that, for about 2 decades at Berkeley. He has worked on a variety of problems of compact objects, plasma astrophysics, formation of galaxies. He has had numerous prizes, the Warner Prize from AAS, the Quataert Fellowship, and he's a member of the National Academy of Sciences, the American Academy of Arts and Sciences. So, without further ado, you're going to tell us about the fate of stars orbiting too close to massive black holes. Thank you.
Great. Thank you. It's great to be here again. So please do feel free to, whoops. So feel free to ask questions as we go, of course. So I'll tell you a little bit about work that we've been doing on understanding what happens when stars orbit very, very close to supermassive black holes. I'll motivate a little bit why that's an interesting problem. A lot of the work that I've done on this is actually in collaboration with Itai here. For those who don't know him, that's also Itai there. He's going to be coming here as a Hubble Fellow in January, and also Wenbin Liu. And this person is the same as this person. You can tell by the haircut. That's Philip Yao, who's a graduate student at Princeton, who's been doing a lot of this work as well. So let me just start the stage by showing you a movie you've probably all seen versions of. This is the stars orbiting the black hole at the center of the Milky Way. The shortest orbital period of the stars that have been detected so far orbiting the center of the Milky Way is about 15 years. And we're going to be talking today about stars that have orbital periods not of 15 years, but maybe 15 hours or something like that. So much, much shorter than any of the stars that are seen in this movie. So the motivation for this is some developments in transients in galactic nuclei that I'll get to. Maybe before we get to that, I'll give you a little roadmap of what this is not an exhaustive description of all possible fates of stars orbiting very, very close to supermassive black holes. But one of the fates we'll talk about is the star just eventually starts to lose mass due to the tidal gravity of the black hole. And that accretes on a timescale of tens of thousands of years or something like that. So that's this sort of quiescent, slow accretion by the central black hole. The other possibilities that we'll talk about are a little bit more dramatic. It's the star being tidally disrupted on more like a dynamical time rather than slowly accreted on timescales of thousands or tens of thousands of years. So this is a version of something you may have heard of stars being tidally disrupted by black holes at the centers of galaxies. There have been a lot of these discovered, but those are usually stars coming in on roughly parabolic orbits, not stars that are on very tightly bound. So that's the distinction that I'll say a little bit about. And then the last possibility that I'll talk about is a star that repeatedly collides with an accretion disk and loses mass during those collisions. And that slowly grinds down the star over a period of time and ultimately could destroy the star, in the process producing some repeating periodic transients at the centers of galaxies. So that is sort of the motivation that got me interested in thinking about this particular problem was
who puts you on this circular orbit? Because for hyperbolic, just chance puts you on an orbit which leads to tidal disruption.
Yes.
But who puts you onto a small elliptic orbit?
We will get to that. Yes.
Okay.
So we'll talk about that, about how the star gets onto this very tightly bound orbit. So what motivated many of us to get excited about this problem was actually the growing discovery now of periodic sources at the centers of galaxies. So this is an example. This is the center of one particular galaxy, Assassin 14Ko, where every 114 days there's a flare of radiation. This shows you the optical light curve. Each of these actually radiates a large amount of energy. It's something like 10⁻³ and sun c² of energy in every one of those flares. This is sort of the most dramatic example of a periodic repeating source discovered in the optical, but there's, of order 10 or so similar sources that have been discovered just by monitoring the nuclei of galaxies. This particular source, when it was first discovered, actually was thought to be an exploding star, thought to be a supernova at the center of a galaxy, but then 114 days later it did it again, so they ruled out that interpretation. So we'll talk about what might actually be producing this. Then I think the thing that actually got me particularly interested in this problem was the discovery of what are called quasi-periodic eruptions. So these are now largely, in fact, only so far detected in the X-rays. So this is an X-ray light curve of the center of a galaxy, where now you have a source that's repeating on a time scale of hours to days. So much shorter orbital periods. The optically selected events are all these longer time scales of months. The X-ray selected events are shorter time scales. Partially that's probably a selection effect having to do with the observations, but there are probably physical reasons for that distinction too. So these are even more remarkable because you're looking at the center of a galaxy, and every 3 hours its X-ray luminosity brightens by a factor of 10. Some of you may have heard of something that's called a QPO, a quasi-periodic oscillation. This is something that accreting solar mass black holes do, where if you take a Fourier transform of the light curve, you see a kind of periodic-ish signal, but those are 1% flux modulation. It's not factor of 10 flux modulation. So this is something completely different in character from what we've known so far. So there's, I would say, largely two broad classes of models for these events at this point. One is that this is a manifestation of an instability of the accretion disk around a supermassive black hole, and that instability might manifest itself in some very large amplitude time-dependent accretion onto the central object, which maybe can produce something like this or something like this. We do know that accretion disks around black holes have a variety of instabilities. They're the ones we know about. There might be some we don't know about. There are instabilities of radiation-dominated disks. There are instabilities associated with disk warps, especially if the warp disk is irradiated by a central source of light. Personally, I'm not a huge fan of these explanations, partially because essentially every accreting system that we know of, every luminous accreting black hole, accretes in the regime where it should be subject to this instability. So why would only this tiny rare fraction of systems manifest in this remarkable way, the instability? I also think it's just very unlikely that an accretion disk instability will produce something as nicely periodic as the signals that are seen. I freely acknowledge that those are not super strong arguments against this possibility. There's a lot we don't understand about accretion disks, so I think this is a possibility we should still worry about. But for those and other reasons, I'm going to focus on this possibility really in the course of the talk.
Is a complete non-expert on this. So when you say that these are rare, we only see that in a small fraction of AGNs, I guess, but couldn't there be something like a jet which is beamed in a particular direction?
Yeah, so that's also an interesting possibility. Is could this be associated with, say, precession of a jet, which is coming into our line of sight only on certain timescales? So in both of these cases, the spectra are thermal. So this is thermal blackbody emission in the optical, and this is actually really astonishingly for accretion disks around black holes. This is thermal X-ray. X-ray emission usually is not very thermal. See emission from accreting black holes. So it really doesn't look like it's a jet, but in principle, absolutely. Okay. So the possibility that I'll focus on, which I think most of the community is focused on, partially for the the theoretical reasons I gave you, and partially because it would be really cool if it's the right answer, is basically that there is an orbiting star or potentially an orbiting compact object, white dwarf neutron star, black hole, and that either, once in orbit, a little bit of mass is being stripped by tides from the black hole, and that's powering a flare of radiation. So that would be what is sort of loosely called a partial tidal disruption. The star is not ripped completely apart. We just strip a little bit of mass off the surface once in orbit at pericenter. So that's one sort of class of mechanisms for producing this kind of periodicity. And then the other possibility is stars actually colliding with accretion disks, and that collision producing sort of an explosion of debris, and that cloud of debris powers the flares of radiation that we see. And that model has been particularly beautifully elucidated by Itai and Brian Metzger, and we'll talk about versions of this as we go. Okay. Part of the reason for the interest in this is that the answer to Andre's question of how did the star get onto this very bound orbit is also interesting for a whole other set of astrophysical reasons, in that one of the very interesting gravitational wave sources for future facilities like LISA is to detect solar mass compact objects, white dwarfs, neutron stars, and black holes, orbiting around a supermassive black hole. These are called extreme mass ratio inspirals, solar mass compact object, 10 to the 5 solar mass black hole. And those are interesting as a gravitational wave source because unlike equal mass mergers, where you don't get that many orbits to map out the structure of space-time, here you get many, many, many orbits to map out the dynamics of the space-time of the more massive object. And some of the stellar dynamical processes that put stars onto very bound orbits are related to the processes that put compact objects onto very bound orbits. And so there's a lot of interest in the phenomena that we'll be talking about, not just from the producing the electromagnetic emission that we see, but from the stellar dynamics point of view of how do you get the star there? What does that tell us about stellar dynamics in galactic nuclei? How does that inform our understanding of the possible gravitational wave sources? Okay. So a lot of what we'll be talking about today is going to be about stars getting closer and closer to the tidal disruption radius, the radius where the self-gravity of the star is comparable to the differential tidal gravity associated with the black hole. That's this radius here. There's another way to think about this process of tidal disruption. If you have a star coming in on a parabolic orbit, such that the initial energy of the star far away from the black hole is roughly 0, then when the star is tidally disrupted, the gravitational potential energy difference across either side of the star is just given by this here. So it's basically the same expression as the tidal force, just not different in 1 power 1 over r. But that difference turns out to be interesting because the difference in gravitational potential energy across a star that's being tidally disrupted is larger than the self-gravitational energy of the star by the mass ratio of the black hole to the star to the 1. So what it means, if you have a star coming in on a parabolic orbit with 0 energy, when it's disrupted, the whole system still has 0 energy. So the disrupted star has 0 energy. But one side of the star has a very negative energy given by this value. The other side of the star has a very positive energy given by that value. The sum is 0, but it means that half of the star has been unbound from the black hole and half of the star is now bound to the black hole. And so the tidal disruption of a star on a parabolic orbit produces this spray of debris where bound material comes back typically on a timescale of a few weeks to a month. That's the characteristic orbital period associated with this particular gravitational binding energy per unit mass. And then the other half of the star is flung off at about 10,000 kilometers a second and just flies away.
But is it really, Eliot, is it really like half and half? Because at the moment of tidal disruption, potential energy of attraction is still comparable to the tidal thing. So this half and half is to be understood poetically?
No, the half and half is actually pretty good, but you're right. If your pericenter distance is, 25% bigger than this radius, then it won't be half and half. If your pericenter distance is half of this radius, then it actually is pretty close to half. So you're right. As you approach on a parabolic orbit the tidal radius, there's a range of radii where you only strip a little bit of mass, where actually you have a bound core left behind. And so it isn't really half and half, but in the limit where the pericenter distance is, a factor of a couple smaller than this, then it is roughly half. Okay, so these stars being disrupted from parabolic orbits have become sort of an industry in astrophysics. We've now detected something like 100 of these in optical or X-ray time domain surveys. The details aren't critical, it's sort of what it looks like. It's quite bright. These get to be significantly brighter than a normal exploding star, a normal supernovae. They last for a few months and then they fade away. This particular one that's shown here in the solid and squared black symbols is interesting because this is actually one that repeated. So it looked like one of these single off star being ripped apart events, but then 3 years later, the same thing happened again. So that's sort of bridging the gap between what we thought were these one-off disruptions and what seems to be some periodic phenomena. So now there's actually a very interesting question of how many of the things that we thought were actually single complete disruptions of a star might have periods of 10 years. We just haven't seen the next event, or periods of 100 years. And it'll take a very long time to see the next. So there's a big kind of interesting uncertainty in interpreting some of what we're seeing now because of the discovery of the periodic versions.
Periodic or repeating?
Yeah, sorry, that was the slip of the tongue.
Okay.
Repeating, yeah. So in most cases, we have like 3 or 4. It's really hard to say. So, yeah, good.
And there may be a fraction of those that do not repeat, but they're also partials or just a fraction of the star.
That's right. You could also have cases where if the star really does come in on a parabolic orbit, but it's only partially disrupted, it is actually often slightly bound to the black hole after that because energy from tides gets taken out of the orbit into the star. But that would be on a very long orbital period that we would not see it repeat in any of our lifetimes. So you need to be on a bound orbit in the first place to have a chance of seeing one of these repeat. Okay, so now to confuse the cosmologists even more with phenomenology, somewhat remarkably, this quasi-periodic phenomena, this time actually quasi-periodic, of these X-ray flares happening every few hours or few days, actually seem to statistically be associated with galaxies that have just undergone one of these things that is interpreted as a star being tidally disrupted by a black hole from a roughly parabolic hole. So 2 phenomena that seem like they should have nothing to do with each other, weird day-long X-ray outbursts by factors of 10, and month to year-long optical flares that are interpreted as a star being ripped apart by the gravity of the black hole are actually statistically correlated.
So they just happen to be doing
So I'll give you, unfortunately not my beautiful explanation, I'll give you Itai's beautiful explanation for this a little later in the talk of why we think this correlation is there. So
Well, why were they looking at this galaxy?
they were looking at this galaxy because Itai predicted this.
Okay, that's a good reason.
Yes, so I'll come back to that. So this is not a completely historical narrative. But, yeah. Okay. All right. So So that's a little bit of context. So these are some of the fates of stars that we're going to talk about. I'm going to now talk a little bit about Andre's question of how do you get the star bound to the black hole in the first place. So our best guess, although this is very much an active area of work, but our best guess is that this is through a process of a binary star coming in and the binary being tidally disrupted by the black. So here's the idea. You have a binary come in. The argument is exactly the same as the disruption of the star. What we want to do now is we want to use the tidal gravity to rip apart the binary, not to rip apart the individual stars. Our condition to do that is exactly the condition we wrote down before. And for the same energy reasons that we talked about before, what we're going to inevitably conclude is that half the binary is unbound, half the binary is bound. What that means in practice is one star gets kicked out of the system at a high speed. That's a potential source of what are called hypervelocity stars, basically high stars leaving the nuclei, high velocity stars leaving the nuclei of galaxies. And the other star remains bound to the supermassive black hole on a much shorter orbital period than it would have had, than the binary would have had coming in. We don't exactly know the rate of this, but I would say sort of an upper limit on the rate, probably of order this, is that 10% of stars are in binaries. So 10% of stars that happen to get kicked in from far away won't be single, they'll be binaries. And so the rate of this process of forming stars kicked out or bound to the supermassive black hole by this process is something like 1/10 of the rate at which stars get kicked in and get tidally disrupted.
But I don't understand. The cross-section for tidally disrupting a binary should be much larger.
So this depends. There's this full loss cone, open,
Right.
empty loss cone regime. So in this limit, the actual cross
Quite how fast you refill it.
exactly.
It's not the cross.
Not exactly. That's right. So
Which
that's
is counterintuitive, right?
that is,
Even
what Andre's saying is the counterintuitive thing is that to disrupt the binary, that has a much larger area. And so you think the cross section for that would be substantially larger, which is true. But the rate limiting step is the rate at which you're kicking the stars into low angular momentum orbits. That's set by a two-body relaxation timescale at large radii. That doesn't care about whether you're a binary or a single star. And it doesn't really care about what pericenter distance you get kicked on. So that's why, again, in a certain regime, this is the rate is not a function of the ratio of the binary radius to the radius of the star. So the tightest the tightest bound star you can get out of this is if you allow me to be extremely optimistic and say that my two stars coming in were touching. Okay, so the binary semi-major axis is like twice the radius of the sun. That's the tightest binary you could have coming in. And then if you work out the estimates of the binding energy of the star that's left behind, you get a star with a period of about 100 days and an eccentricity of 0.98 that's left behind, the bound star that's left behind by this process. And of course, if the binary is wider, then in general, the eccentricity will be higher, the orbital period will be longer. So this is sort of the lower limit. This is tantalizingly similar to the period of this particular system, 114 days. We don't know if that's a coincidence or not, but this is sort of.
Of course, it is a coincidence because it has been there for hundreds of years, right? Didn't it go down?
What do you mean go down?
Because you have P over P dot over there, right? It is today, it is this small period, but in the past, no?
So I think it. Okay, I don't actually remember. Do you remember? Was there anything earlier? I think we don't know. So I think we don't know whether it just started here or was there for a long time before.
It just started at the beginning of Assassin.
No, it started when Assassin. I'm sure it was there for some amount of time. It can't have been there that long because this time scale is quite short. Right.
Well, the other way,
Could
maybe
you
the way
have started with a
started
period
without.
of 1,000 days and get here
Actually,
without
that's
moving
not,
much?
you could, that's not, I mean, that requires then some very long time scale associated with gravitational waves, exactly, that's what we'll talk about. You can't get this from gravitational waves. Sorry, there was another question.
That's kind of separate, maybe, those binaries that are coming to be tidally disrupted. Do you know, or people know what are the masses? Is it more likely to be small mass stars or high mass stars?
It's much more likely just because of the lifetime to be lower mass. Because the high mass binaries, the chances that they'll get an appropriate angular momentum kick to put them onto a small pericenter binary orbit is low. So they're more likely to be lower mass.
Although the only stars that we know of that actually have undergone this high masses
are B stars. Yes. Yeah, that's fair. That's fair. Thank you. So they should be low mass stars, but they're not.
How many sources of this 100 days period have you observed?
So this is the most spectacular in the sense of having the most repeating flares. I think there are 7 or 8 optically selected events that have multiple flares.
So in the formula you wrote just before the period being 100 days, why doesn't the mass of the black hole drop out just from Kepler's law? Like P squared goes as RB cubed over M black
Because
hole.
the binding energy across the binary depends on the black hole mass. Depends on mass ratio. So it's that mass ratio still comes in. Okay. Anything else? All right.
Maybe you said it, but why will they be so tightly binary when they arrived at the tidal?
So I definitely did not say that. Maybe I did not explain why. So this was just to give you a sort of, this is the most bound you could get. There actually is a very interesting dynamics problem that happens if you have a binary orbiting around a supermassive black hole. You get a version of quasi-Lidov oscillations, which can cause the binary to shrink. And as Yuri showed, actually can cause, in a number of cases, can cause the two stars to merge with each other. And so it's actually quite likely, although this hasn't been calculated in great detail, it's quite likely that tight binaries, i.e. the two stars are close when they come in, are overrepresented relative to the field population because of essentially quasi-Lidov type event. Okay, so now I'm going to sort of skip the stage where the star has now been created on a bound orbit, and it's going to get closer and closer to the supermassive black hole. We think it gets closer to the supermassive black hole by a combination of 3 physical effects. So one is gravitational wave orbital decay, which sort of relentlessly brings it closer and closer. Another is continued angular momentum diffusion by interacting with other stars that are in the vicinity. And the third is actually drag due to the star colliding with an accretion disk that may be present in the system. That gas drag can dissipate energy and help the orbit shrink. And the relative importance of those 3 processes will determine how many stars that are created by the mechanism that I've just described to you here end up approaching the black hole on a very eccentric orbit or on a circular orbit, etc. And we don't understand very well that partitioning of those different possibilities. So I'm going to take you through some of the different fates of stars that have been created on these very short orbital periods, but I'm not going to address kind of the relative rates of those different processes because I think that part is actually a very interesting and not super well understood stellar dynamics part of the problem. Okay. So the first thing that I'm going to stress is the effects of tides raised by the supermassive black hole on the surrounding star as the star gets closer and closer. So let's imagine, just so you have a sort of physical picture, that it's just gravitational waves bringing the star closer and closer to the black hole. As the star gets closer and closer to the black hole, it starts to approach the tidal radius, its pericenter shrinks, its eccentricity also decreases by gravitational wave radiation, right? And as it gets closer and closer to the black hole, the tides raised in the star get larger and larger, and they start to affect the structure of the star. So just to give you a sense of the energy dissipation in the star due to tides raised by the supermassive black hole, this is an estimate of the energy dissipated by exciting waves in the star due to the time-varying gravity that it sees orbiting around the supermassive. So the pericenter distance relative to the tidal radius is this ratio here. This is the eccentricity of the orbit at a given time. And then the power gamma here depends on the details of the waves that you're exciting. Is it internal gravity waves or what are called inertial waves if the star is rotating? Doesn't matter. That's sort of a not critical detail for this. The important thing is that this is a large number because tides get weaker quickly as you move further away from the black. So the way to think about this is that as a star approaches the black hole, gets closer and closer, because of this very steep power law dependence and very large prefactor in front, right? This is an enormous energy by normal stellar standards. What happens is at some point, the energy that tides are putting into the star goes from being negligible to being very important and changing significantly the structure of the star. And the exact radius at which that happens, depends a little bit on this uncertain prefactor and this uncertain power law index. But because this is a steep power law, it's, roughly once the pericenter distance is less than 4 or 5 times the normal tidal disruption radius, the star will start to get heated by tides at a rate that's much larger than what fusion is doing. And that will start to completely change the structure of the star. And really the only way to avoid that is to have the orbit be fully circularized by gravitational waves by the time it reaches this distance. If there's any residual eccentricity, this is hard to avoid. And that then creates a runaway process where the star is now being heated on the inside by more than it was in its previous billions of years of life. And so its radius will expand. That'll make it more susceptible to tidal heating. If the radius has gone up, that'll cause it to inflate even more. And so it'll inflate to the point where it starts to now lose mass to the black. So basically, once you reach this distance, what will happen is the radius of the star will go up so much that you'll effectively start to undergo mass. So we've created a very funny binary of like a solar mass star orbiting a million solar mass black hole and transferring mass to. Transferring mass mediated by this process of tidal energy dissipation inflating the star. And there are really 2 possible fates for this binary, which are the same as the fates for normal stellar binaries. When you have mass transfer in normal stellar binaries, one possibility is that the process is stable. And the way to think about that, just very roughly, is that if the star's intrinsic dynamical response to losing mass is that it shrinks a little bit in size, its radius decreases, then that is a stable mass transfer process because it makes it more resilient against tidal stripping. The star shrinks as it's losing mass. So in this regime, the rate of mass transfer is set by whatever process is either forcing the star to get bigger or forcing the orbit to shrink. So in normal stellar binaries, that would be gravitational waves causing the orbit to decay. That's what happens if you have 2 white dwarf binaries, for instance, that start to undergo stable mass transfer. In the case we're interested in, it's a little different because you have this tidal heating that is unique to the very high mass ratio system. And so in this regime, the star gets accreted on roughly the time scale that it takes tides to double the radius of the star. And that, unfortunately, that time scale we don't know very well. It depends on some of the microphysics of tides that's not fully understood. But our estimates are it's something like 1,000 to 100,000 years. So this would then be a supermassive black hole accreting from a star at a rate of like 10 to the minus 3 to 10 to the minus 5 solar masses a year, which would actually be very typical of what we see low luminosity active galactic nuclei doing in nearby galaxies. So this could be a way of generating sort of long-lived accretion, not by having some molecular cloud come in from the interstellar medium, but rather having a star spiral in and undergo this process. This is just to say that you can calculate a lot of this analytically. You can also calculate all of this in a stellar evolution code. So we actually took the mesostellar evolution code, added in this tidal heating in the interior of the star, and then evolved the star as a binary around a million solar mass black hole. And this shows the mass transfer rate from the star to the black hole as a function of time. It's in this ballpark of, in this case, about 10 to the minus 4 solar masses a year. That goes on for 10,000 years or so until at this point, obviously, something dramatic happens and the accretion rate starts to go up very dramatically, and the mesostellar evolution code crashes. You don't know if it crashed for a physical reason or because Mesa's pain in the ass. It turned out in this case it was for a physical reason, which is at this particular time, given the structure of this star, the mass that this star had been whittled down to, the mass transfer switched from being stable to unstable.
So I wanted to ask about the accretion rate versus the low luminosity AGN that you
Yes.
showed. So I understand that these accretion rates sort of are in line with what we infer in low luminosity AGN, but is the emission in this case similar? So do you actually form something like an extended accretion disk? And would you get something similar?
Right. So I think the prediction here is that you would create, you would first create a very compact disk. For those who know about AGN stuff, you wouldn't have a broadline region. The disk would be too small. Some of the disk would spread to larger radii over time, but you're absolutely right that this should look actually spectroscopically different from a normal AGN, in particular, in not necessarily having stuff out at 10 to the 4 nm. There should be a compact inner disk, but less of the normal stuff at larger. That's exactly.
And maybe this is beyond the scope, but do you so this process for a single star lasts 10,000 years. And typical, I don't know exactly what kind of galaxy are at the center of here, but
Right.
do you expect this to it's 10,000 years and then that happens every 100,000 years, or
Right,
is it
so-
constantly happening?
So that's back to sort of the rate question. So I
Yeah.
think the rate number that we are more comfortable with is, something like once every 100,000 or a million years, stars get kicked onto these bound orbits. If a non-negligible fraction of them undergo this route, that could be 1% of galaxies
Which is 10% of AGN.
doing something like this, which could be a not uninteresting number. That's exactly.
No, but are you really saying that 10% of AGN are powered by a single star?
I am saying, I think that, so I'm saying that's an upper limit. But I think it could easily be that a few percent of AGN are powered by a single star. Yes.
And as Magda is saying, they
Yeah.
should look different from other AGN or something.
Which they do. Most low luminosity AGN don't have broadline regions. They don't even have narrow line regions, right? They're linear.
Yet you are not saying that all low luminosity
No.
AGN are powered by a single
No,
star.
that's right. That's right. But I think it is
Wouldn't it
absolutely
be nice to really
Yeah, it would be-
see this class of
Yeah, so there is a prediction that the optical UV SED of this disk should potentially look different than other disks. the problem is we don't understand the optical UV SEDs of normal AGN, and so that prediction, I think, is difficult to test at this point. Yeah, so I would say the predictions of actually carrying this through to what it means for the population of low luminosity AGN, and can you rule it out from what we know, or can you rule it in? We have not followed that through at this point. Okay. Yes.
Coming back to the more massive stars, the plot you showed was for solar mass star.
Yes.
Would you think that if that was, I don't know, 20 solar mass star, it can do something to the star, like speed up the core collapse?
That's an interesting question. So what actually happens, this is a very fun stellar evolution problem. You add this additional energy into the star expands, that actually causes the core to cool down, you shut off nuclear reactions. You don't need the nuclear reactions anymore to keep the star inflated, you have another source of energy. So I haven't done the case of a massive star, but I assume if it was not highly evolved so that it already had like a super dense core which would be immune to the tides, if it was like a main sequence massive star, the same thing would happen. It would shut off hydrogen, or if it was helium fusion, you would shut off helium fusion. And then exactly what the subsequent evolution is interesting. I don't know if you whittle it down to one solar mass. I mean, in principle, you can just whittle it down all the way to nothing. Exactly what happens towards the end, I'm not 100% sure, but I think you could definitely have it, if you had this going early in the evolution, you could have it avoid any of the late nuclear burning stage. Yeah. All right. Okay, we're going to have to go through the unstable phases very quickly. So the other possibility is that a star, as it loses mass towards the supermassive black hole, if its intrinsic response is to expand its radius, strip mass off the star, imagine the star wants to expand its radius, that's an unstable process and you get runaway. And in the stellar binary language, people would say this is a stellar merge. Have these two stars, one starts to transfer mass onto the other, it's unstable, and they. So what that will do is you'll have sort of a power law increase in the accretion rate from the star to the black hole, and at some point that really goes into a complete runaway, and on a few dynamical times the star gets shredded and forms an accretion disk around the black. And then the highly sophisticated numerical simulation that Itai and I did, as illustrated here, sort of sketches out what we think happens in this process. It's quite interesting. The star is sort of transferring mass onto the black hole. The mass transfer rate is increasing dramatically. At some point, the mass transfer rate goes above Eddington. And so now you start driving strong winds out of the system. The mass transfer rate ends up so much larger than Eddington that you actually inflate a very large optically thick envelope around the black hole. That outflow eventually subsides as you've either accreted most of the star or blown most of the mass away. And then you're left behind with some residual accretion disk, which over some time scale of tens or hundreds of years will dissipate and accrete onto the black. So this is the tidal disruption of a star by a supermassive black hole. It's exactly what it is. It's just coming in on a circular orbit, not on a parabolic. And the exact time scale that all of this happens on depends on the viscous time and the accretion disk that you form. So it's a little bit uncertain, but it's a time scale of a few weeks. That's what we think roughly. The time scale in particular of this phase of very high accretion, producing this very optically thick outflow, and then that all fading away is sort of a few weeks to a month. So what we think that would look like observationally, just to give you a sense, is there would be a bright X-ray source for years prior to this happening. That would be this phase, right? There's accretion being fed onto the black hole. The accretion rate is ramping up. For a while, it's below Eddington. You can see down to the black hole. You get a bright source of X-rays. And then in this short period of time, when you create this very large opaque atmosphere because you have strong outflows, the X-rays would disappear and you would get a bright optical UV source associated with this optically thick and shrouded cloud of gas going. So this is unusual, right? This would be if imagine you had an optical survey for transients, you would see this thing, but then you would go back and find that there were X-rays there a few years before, which is not what you usually find when you see, you know, bright new sources of optical light appear on the sky. So this is sort of a unique signature that we hope will be detected. Okay. So you may notice I didn't tell you which of these I think happens. I said there's a stable possibility and there's an unstable possibility. We actually know what determines which of these two regimes you're in. It really depends primarily on whether or not the star is convective or not. So this is known from standard binary evolution. Fully convective stars, because they have constant entropy throughout, when they lose mass transfer quickly and respond adiabatically, they expand in size. So they are unstable. Radiative stars don't have constant entropy throughout. They have the entropy gradient created by whatever photon diffusion wants to set up. When they lose mass quickly, that's still an adiabatic process. But because there's an entropy gradient in the star, they typically actually respond by shrinking. So which of these outcomes depends on whether or not the star is mostly convective or mostly gradient. You might think we know that because we understand stars. The problem is we don't understand stars that have been tidally heated at a rate of 1 million times the luminosity of the sun for hundreds or thousands or tens of thousands of years of evolution. So the question of whether the star is convective or radiative is not just a question of how big this number is, it's where in the star is all that energy deposited. And that's a much harder tidal physics problem. And so we're not actually sure as a result which of these is the most likely. That's sort of a coupled tides plus stellar evolution problem that we have not solved.
So you can tell which the latter of these three, the last two, you can tell by convexity.
By
You said one is radial and one is
radiative.
radiative.
So this case is more likely if a star has most of its mass being convective. In this case is most likely if a star has most of its mass.
Oh, so convective is not convex? Like say like concave down.
Yeah, no. Convective, sorry, is boiling in the interior transfer. Okay. So last topic, we'll go quickly, is the star being destroyed by colliding with the disk enough that the collision strips so much mass off the star that the star gets whittled down. So the first question is, where does the disk come from? So you might think, well, galactic nuclei have accretion disks associated with AGN. Maybe the star runs into one of those. That's a priori unlikely, right? Because accretion disks, dense accretion disks that can affect stars associated with active galactic nuclei are actually relatively rare. So there are sort of two improbable things here, pre-existing AGN and then the star getting really close. That's actually not statistically very likely. One possibility is actually the star creates the disk that it then collides with, right? This unstable mass transfer process can create a very dense disk that the star can then collide with. So that's actually an interesting possibility. It's not very well understood how that would work. The possibility that has been the most interesting is this very nice prediction of Itai and Brian Metzger that actually it's a completely unrelated parabolic tidal disruption that creates an accretion disk around the black hole. Now, I think if you didn't work in this field, you might react to that by being a little skeptical of Itai's beautiful prediction, because it seems like this is just as improbable as this.
But sorry, what is his prediction? So he's saying that the disk was created by tidal disruption, and then another star came in.
Yes.
And why would the second star come in?
So this is the beauty of the prediction. This was the thing that I did not recognize that Itai and Brian recognized, that I wish I had recognized, which is that the time between parabolic TDEs, roughly every 100,000 years in a galaxy. And if you have a star orbiting at 5 times the tidal disruption radius with a period of a few days, the time for it to spiral in by gravitational wave radiation is 10 to the 6 or 10 to the 7 years. So once you get the star there, it is inevitable that the star is going to have to interact with a lot of TDEs. So in that direction, you're not guaranteed that if you have a TDE, you have to have stars orbiting near it colliding with the disk. But if you get the star there orbiting close to the black hole, it is actually kind of inevitable that it has to collide with a bunch of disks created by it. And this motivated people then.
So you're saying stars are always there, you just need the disk.
Yes, or if more, it's more of an if then, but there are enough stars there. If a star is there, there will be disks there. That's the prediction. This motivated people to look for, because there were models in which these QPEs, these X-ray flares, were produced by collisions between stars and disks. This motivated the observers to follow up optically selected TDEs a few years later to look for X-ray flares, and that's exactly what they found. So this was 4 years after an optically selected TDE. Suddenly,
the sign of this is a little funny, right? Because you're saying if there's a star, there's an extreme mass ratio inspiral, it'll have a lot of TDEs.
Correct.
The test you're doing is the opposite.
That's correct. So,
so this is sort of saying you're getting the fraction of things with you do a bunch of TDEs, you observe this way, you're getting the fraction of them that have that assuming all this is right.
That's correct.
Have an extreme mass ratio.
So the prediction you would really want to make is what is the probability that any galactic nucleus has a star with a period of a day at a given time? That's back to this much harder stellar dynamics rate question that we don't exactly know that. So I think the solid part of it is the direction I gave it to you here. The harder part of it, which is actually, I completely agree with you. If you want to go from take TDEs, observe how many of them have X-ray QPEs 4 years later, to some constraint on models, one has to do the prediction, not just in the direction I gave it to you here, but in the direction that you're asking. That's exactly.
But you could, there are many more galaxies which have a dense AGN disk. Why not do you not make the same?
Actually, well, I think there's a variety of issues. You know, most low luminosity AGN are not dense disks. They're big puffy things that the star moving through it is not affected by. Low density disks like the Galactic Center, M87, right? And then I think the biggest worry, the big advantage of TDEs here is that if you have a big AGN disk that extends out very, very far away from the black hole, how did the star possibly make it down to a 1-day orbit? It would have been destroyed by collisions at a 10-day orbit or a 100-day orbit or a 1,000-day.
That's a prediction.
So the advantage of the TDEs is that it creates this compact disk so that the star could make its way by all of these processes down to 1 day, not have been destroyed before that, and suddenly interact with it. So that's how it sort of, I would say, all hangs together.
You're saying it requires a compact disk.
I think a long-lived AGN disk is not conducive to getting a star down on a very short.
Maybe he was just lucky.
No. You'll talk to him more and you'll realize he's not just lucky. Okay, so
How long do the QPEs should be detectable? Like how long in time
right. So
after this?
the calculation, so there's many effects that come into that. 4 minutes. Which of these? Okay, I'll say a few things. So how do we think that the star colliding with the disk produces X-ray flare radiation? Then I'll come back to this. So the calculation that we've done, this is now going to be a numerical simulation. You can make some analytic progress on this, but it's a tricky problem, is we've basically taken a star and repeatedly slammed a disk in. So this is our star. It's just a little outer part of the star because the shock doesn't propagate very deep into the star. So we didn't want to waste numerical resolution in the interior of the star. So we just simulate the outer tenth of the radius of the star. And then we slam a disk into the star repeatedly. The beautiful thing about this problem is you can actually do it on the right time scale. Right, the dynamical time of a star is about an hour. You want to hit it every 10 hours. You can do that in a simulation. It's not such a crazy ratio of time scales. So what the movie is actually showing you, color is basically bound or unbound material. So the outer parts of the star get puffed up by the collision with the accretion disk, and every collision strips off some mass. So I think that one thing we can calculate with some confidence is that in collisions that are sort of in the ballpark of what we think you need to explain these X-ray flares, a star could survive maybe 100,000 or 1 million of those collisions before it would have lost so much mass that it would just. How long that is in years is much harder to answer because that depends on how long the accretion disk created by the TD sits there. If the accretion disk were always there unchanging, that would correspond to 100 or 1,000 years. But the disk spreads, kind of accretes away from the black hole, and so probably is not there for hundreds of thousands of years, continuous.
But the argument that Mike is asking about AGN disk and this.
Yes, exactly. This time scale. This is why it's so hard to get the star to a tightly bound orbit if you have a long-lived AGN. That's exactly. Now, this timescale gets longer if you're colliding with the outer part of the disk, but it's still, shorter than the stellar dynamical process.
But you can make this argument for the star, which is already there.
Sure.
You can say that if the star is on this 10-day orbit, 10-hour orbit, then it wouldn't be able to live for longer than 1,000 years in that environment.
Yes. Okay. So then just the last thing I'll tell you, how do we think the flare of radiation is produced? So you have this sort of cloud expanding away from the star. That cloud gets tidally stretched by the gravity of the supermassive black hole. And then half an orbit later, that tidally stretched debris slams into the accretion. So this is a sort of illustration of some of the processes in a paper with Itai and Brian recently. So again, star collides with the disk. You create initially a spherically expanding cloud of stellar debris that's unbound from the star. That gets tidally stretched. And then that tidal debris comes back in and collides with the accretion disk half an orbit later. And you can think of what this does, this collision basically creates a hot wind, which now expands away from the collision point. And that hot wind is driven by the energy associated with this collision, and it lasts for a time scale set by the length of the stream. And so we've calculated both analytically and numerically the properties of this sort of shock debris produced by the stream colliding with the disk.
This is your flare, supposedly.
And that is our prediction of what is actually producing the flare. So this is in simulation of this process, the details of which I'm skipping. These are simulations that don't include radiation. So the thing that we can calculate easily in the simulation is how much mass is shocked as a function of time. So this is sort of m dot of shock mass. And if we assume that m dot v squared, that's the shock energy, if we assume that 10% of that goes into radiation, just to give you a sense of luminosities, this would be the luminosity of the flare here. This is the thing we actually calculate in the simulation, is the m dot. And this can produce, in this case, for an orbital period of 30 hours, this can produce a flare of a few hours with about the luminosity that's seen in the observations. And then if I just repeat that once every 30 hours, this sort of has the right luminosity and right duty cycle to explain the flares that are actually seen. So that's the process we think that is actually producing the flare, is that you have this sort of cloud of shock debris that, as it rains back onto the disk, creates effectively an explosion that expands back out and produces a flare of X-rays, the duration of which is set by the time for this debris stream to collide with the disk, and the brightness of which is set by the kinetic energy m dot v squared of that debris cloud interacting.
Don't you expect a little something when the star crosses the disk, like interflare, so to speak?
Right. So let's see. Yes. So there's a couple of things that are interesting here. So actually, in this numerical calculation, this broader part of the flare is produced by the stuff that is the gas that is not bound to the star, the stuff that's been tidally stretched. There's a narrower core that is actually produced by a gas that's within the Hill sphere, within the Roche lobe of the star. That gas is a bit denser, it produces a brighter flare. And then I think you're also asking, Andre, about this. Yeah, this should also produce a flare of radiation. That's exactly right. And I think it's unclear whether in a given system,
who is brighter even is unclear.
So I think in general, we think this one is brighter, especially for longer orbital periods. Maybe the better way to say it, radiates more energy. That part I think we're more confident in. So it lasts significantly longer. When the orbital period is shorter, these two can actually be more comparable, slightly coincidentally, in bright.
Wait, Eliot, I'm sorry. I think I'm missing something in this
Yep.
picture related to this. So, okay, we have the yellow sphere. It goes up. It gets tidally stripped. It hits the disk, and then presumably the red goes. Like, is it
It's
just
a new?
okay?
Same thing happens again.
The same thing happens
again,
again and again,
happens
but
again.
it's not symmetric.
It's not symmetric.
Okay.
Well, no, it is symmetric. Sorry, it is. But if we're observing this at a typical random angle,
Yeah.
it's not easy to see the version of this that
I see.
happens
I
on
see.
this
Thank
side.
you.
of the
Thank
disk.
you. Okay.
So what Andre's asking about is,
The-
what about the thing we can see is this
Yeah.
punching through the
When it comes
disk.
through the other side.
And I think the challenge is that in general, this debris stream and this cloud punching through should not look the same. And the observations these look kind of the same. So I would say one way to say this is, in this light curve, are you seeing one flare per orbit or two flares per orbit? We're not sure. There are some reasons in some systems to think we're seeing two flares per orbit, having to do with the timing that I didn't go into. There are theoretical reasons. The sort of model I described to you would suggest that one of them should be substantially brighter than the other. So maybe we're only seeing one flare per orbit. I think this is actually, that binary question is still an interesting question that we're not sure of in many of the actual observed events.
So
Okay.
do you think that this will go back to normal after half period? Or would you have a sort of continuously disrupted this?
Yeah, that's a great question. So the question is, what happens to the disk during all of this? So there's, again, if we go back to, I think there's two answers to that. So this the sort of dense star itself colliding with the disk is relatively localized damage to the disk. And that can probably fill in on a time scale shorter than the orbital period because it's spatially very localized. This kind of larger region that's been crashed into actually does carve out a more interestingly large structure in the disk. And exactly whether that completely fills in one orbit later, because if this is on a roughly circular orbit, everything, the orbital period of the gas and the orbital period of the star are basically the same. I think it's not completely clear as to whether that perturbation gets completely erased or whether there might be some interesting long time scale modulation that you can see in the light curve because you're colliding with a previously damaged disk.
Or you might also have shocks propagating through the disk, right?
You might, that's right. Especially, I mean, I think if this is a 1 solar mass object and a 1,000,000 solar mass object, the shocks propagating through the disk, I think, are not very strong. If it was a 1 to 100 mass ratio system, they would be very strong. But in the 1 to 1,000,000, it's not very strong. Okay, so I'm going to stop there. So these are just a few of the fates that a star can have orbiting very close to a supermassive black hole. Just to end by saying none of these are mutually exclusive. It could very well be that a star has a period of stable mass transfer, then undergoes some collisions with a disk, and then undergoes a period of unstable mass transfer, right? These could actually all happen to the same star in different evolutionary phases. And there's actually other interesting fates that I haven't even talked about, like stars colliding with each other if the stellar density in the nucleus is high enough. So this is a very interesting combined stellar dynamics, accretion, and stellar evolution problem, which is important for understanding not just the kind of interesting repeating classes of transients and galactic nuclei, but also ties in particularly to these classes of extreme mass ratio gravitational wave sources that we hope to be able to see with these. So thank you for your time.
If you have lots of questions, I'm going to officially release the audience. But if you want to, whoever wants to stay here and ask more questions is of course no.
I think you mentioned at the beginning these periodic X-ray observations were very thermal X-rays.
Yes.
Are these debris, like while they have the debris disk interaction producing these X-rays, expected to be thermal X-ray emission as well?
So I think one of the challenges in understanding the spectra is that in many but not all cases, the sort of cloud of debris produced by these collisions is a little cold to explain the X-ray temperatures that are seen. So another nice argument that Itai and Brian Metzger made is that the regime of shock here might be one where actually the photons and gas are not in thermal equilibrium. And so you end up with higher temperature photons than the gas, which helps in explaining the temperatures of the radiation that's actually seen. So that is actually another very interesting part of the problem of actually doing the radiation predictions correctly. The speeds of the shocks here can be 1/10 of the speed of light or 0.03 of the speed of light. And at those high speed shocks, you're not necessarily in purely local thermal. Good question.
You were talking about earlier how you didn't know about the core collapse of stars with these types of in the 3 regimes that you mentioned. Is there interesting physics there like that people do like in these types of problems?
Yeah,
regarding core collapse.
I mean, I think if you really had a massive star enter this regime where tidal heating is important for its structure early in its evolution, I think it would just could avoid core collapse. I think if it did it late in its evolution, the center of the star would be so dense that it would not care about the presence of the supermassive black hole. So the core would undergo late stages of stellar evolution, sort of unaffected by the presence of the supermassive black hole. So I think not having thought about this a lot, I think my sense is that it's sort of a bimodal situation, depending on exactly when in stellar evolution the massive star ends up on this really tightly bound orbit.
I know that we didn't follow up this a lot, but like when you say dense enough, can you give like rough estimate, 10 to the 8 grams per cubic centimeter or before?
Right. So I think the way to say it is that if it's a million solar mass black hole, a white dwarf is tidally disrupted well inside the horizon of the black hole. So I think once the core of the star has reached 10 to the 6 or 10 to the 7 grams per cc, which would be solar mass white dwarf, something like that. I think for a 10 to the 6 solar mass black hole, it's probably not going to be strongly affected. If you go to a 10 to the 5 solar mass black hole, 10 to the 4 solar mass black hole, then you can tidally disrupt white dwarfs. You could affect the core of a massive star later.
Can we talk a little more about, because this thing with a disk, which is dense, it's really too dirty. But what about if you have just a black hole, no AGN, just supermassive black hole and a single star, right? You talked about this thing, right? So basically, like, for example, you said in the beginning, this whole thing is interesting because it can predict, for example, eccentricities of this supermassive black hole, stellar mass binary, stuff like that. Like for this, because this thing seems to be clean enough. Supermassive black hole, a single star, nothing else.
Yes.
Right? You are saying this already is interesting because of tidal heating, basically, and nothing else, right? And it is thinkable that the star is highly eccentric.
Yes.
Correct? That's a lot, right?
Absolutely.
So for this thing, for example, from observations, like what can you measure eccentricity, like this system just as a binary, like you alluded to it. In some sense, it is a binary star. Only the companion here is a little weird.
Right.
So this and for normal binaries, we have a lot of things to say. Like, how can you measure eccentricity?
Right. So what people are trying to do is use.
But this is with the disk.
This is data.
This is data. You're saying this could be my clean system.
Yeah, maybe. Okay. What they're trying to do.
Your clean system.
What they're trying to do is use the timing here to measure properties of the system. So for instance, a few of the observed systems.
Sorry, Eliot, let me interrupt. So these quasi-periodic eruptions, you are saying they do not presume that there is a disk.
I mean, this is just an observed phenomenon.
I understand, but in your interpretation, probably the disk is already
I think
here.
So the motivation for the disk is that, so you might look at this and say, this is just an accretion disk. You fuel an accretion disk, it has a spike of accretion, you wait a little bit, it has a spike of accretion, you wait a little bit. That doesn't work. And the reason it doesn't work is that the period of this system, right, is, I forget what this one is, it's like hours. And the viscous time of an accretion disk close to a black hole is extremely difficult to get to be less than this time scale here, which is what you would need it to be if it's powered by accretion. So it's very hard to see how this can be an accretion-powered phenomena, which is why that has really led to the.
But my question is, can I keep it clean? Is it necessarily that the disk is created? Because once the relatively dense disk is created,
yes,
I mean, that's dirty, and Einstein teaches us not to look at dirty systems. So can it remain clean? Can it remain a binary?
So I think it's very hard. So the way that I would imagine producing with a minimum of complexity, a system that undergoes short duty cycle, large amplitude flares as cleanly as possible would be, you have a star, it comes in on a very eccentric orbit. It has a little bit of mass stripped off. And I just say that that little bit of stripped mass accretes on a time scale much less than orbital period.
But you're saying it's impossible.
I think with these short orbital periods, I think that is not possible. I think that is
Yeah, the optical flares that
completely
repeat
possible
every 100
here.
days.
Because 100 days for the period is long enough that I can make the viscous time close to the black hole be 10 days, produce the flares.
So you're saying this could be a clean binary
This I think is the clean
with
case.
individual outbursts, tiny, teeny disks,
Exactly.
which are accreted before
And
the
that's-
next episode.
That's exactly. So I think that in some sense, that makes this, you're right, a slightly cleaner version of the problem. I think
And the periodicity,
part of why this is
the quality of periodicity here is clearly much better than the quality of periodicity in that system, right? Because if you look at that system, it doesn't look that
Why are you laughing?
no.
It doesn't
I
look that periodic.
agree. It's very irritating. I wish these were much cleaner.
It
periodic
doesn't look that
sources.
periodic. I mean, it looks.
So but this is actually what I was gonna say in response to so imagine that you have an eccentric orbit and you have two flares. Now you expect there to be secular timing variations because the time between the two collisions is not the same. Now imagine the star and the disk aren't in the same plane and the star is undergoing apsidal and nodal precession. That's going to produce secular variation in the timing. So yes, the timing isn't that clean, but there might actually be clues as to the properties of the binary, the properties of the black hole, et cetera, in that timing variation.
But your 114 day, the
is-
114 day is very clean,
is
right,
very
in terms of periods.
But one puzzle about it is the P dot.
Yeah.
Mhm.
So this seems to be like a very natural, clean system.
But
some
maybe it's
eccentric-
eat up enough of mass at each episode so that it can influence somehow the period, no? Possible, impossible?
Really
challenging.
challenging.
Could you have multiple stars piercing through the disk at the same time?
This has no disk.
No, the other one, like for the.
Yeah.
The uneven periods.
Right.
But what-
Maybe, but that would
what-
probably be much.
So
rare.
can I actually follow up on this? And
Yes.
I think I can join these two questions that
Okay.
Yasin and Andre asked. So it is, so you said you don't know how frequently this AGNs have a close companion, but by now we had like 100 tidal disruptions that we observed. One of them shows Eti's phenomenon, or maybe two of them show Eti's phenomenon, but they also show QPEs. Can you say that this means that 2% of AGNs have this close
No, I think it's
companions?
much higher than that because the number that have been followed up is small.
Oh, the number of.
Number where there has been good late time X-ray data.
Oh, okay. So
Yeah,
it
could be-
so
it
it's
could
the
be-
lower bound.
Yeah,
the lower bound.
it's a lower bound.
So it's a lower bound. So
Yeah.
more than 2%. You're
Yeah.
saying that more than 2% of all AGNs, based on the data that we have this close companion, right?
Not of all AGN, of all
TDE.
TDE.
No, but TDE is okay. But TDE, sorry, of black
galactic
hole.
nuclei.
Supermassive black
nuclei.
holes.
Yeah,
Supermassive
good.
black holes. So
Yes.
more than 2% of all supermassive black holes and galactic nuclei have these guardians,
Yes.
right, which are orbiting them at a period of, several
Days.
hours per day, right? That's a statement.
Yes.
It's just that we can see them only. in
We can
TDE.
see them. So question, okay, first of all, back to Andrei's question. Is there any signature? Because of course there are gazillions of these supermassive black holes. And they're all, in some sense, they're all low luminosity AGNs. They all have some low luminosity. Is there any observational signatures that you can come up with? Gravitational lensing, for example, or something like this, which doesn't require the collisions with the disk, but something
I think
else.
the one that has seemed the most promising is the one that you were alluding to, which is the prediction that the emission when there is mass transfer should have an unambiguous signature that there is not all of this gas at larger radii. So you should have gas at, inside of 100 M associated with the mass transference star, and not at larger radii because you don't have some gas coming in from the interstellar medium. And the problem with that, of course, is that only 1% of the radiation gets produced outside of 100 M. Maybe it's 10%, only a small amount of the radiation. So that's like a small perturbation to at least the overall luminosity of the low luminosity. So if we could tease that out, that would be one way to do it. Lensing is interesting. I haven't thought about that.
Because you can have lensing both by the star because large fraction of them would be edge on, right? If all these things, edge on systems are more common than phase one systems. So wouldn't you have gravitational lensing by the star of this compact accretion disk, or by a black hole of the star? I don't know, something like this.
Yeah, that's a good. I think that's an interesting question. But so take the rate seriously, which I think it is, right? It could be tens of % of galactic nuclei should have this. And so what is there some? Yeah, I mean,
I think it's hard to compete with the intrinsic variability and how kind of poorly modeled the emission is.
That's right.
So you want to add perturbation.
And I think the lens, right? You're trying to lens a very big source, which would, be lensing the.
Which one is big? Accretion is horizon scale.
Well, it's horizon scale, but it's a one solar mass object that's doing lens. So in that sense, it's big, right? Because the Einstein, yeah. So it's a very good question. Are there other cleaner tests of the basic stellar dynamics statement that there are?
Guardians of this black hole.
Exactly. I think that's a very, very good question, and I'm not sure what the clean tests. Yeah.
But also, what is the state of your theory if you are not telling me what's the eccentricity here?
Oh, it's 0.97.
No, seriously.
I think it's something like that because the period is this, and I think it's
related to.
No, but the question is, can you measure? If it is indeed this clean system, which is just a binary which occasionally gives a little mass to the black hole, which is then consumed in one accretion episode,
right, so,
is there anything?
Well, that's can
you make it into? Can you give me at least one formula?
Can we make it a pulsar? Right.
Exactly.
Oh no, of course, yes. So that has been the goal, and that's why the timing is so interesting. So that's why we spent a year and a half trying to understand this number, which was not easy to do. So
wouldn't the amplitude of the luminosity have something to do with the eccentricity because of the velocity at which something punctures with this, for instance, if that's the model you're going with?
So I think this gas is at, we know L, we know this is thermal blackbody radiation, we know the radius is quite large, so it's not clean. This is optical radiation that's is reprocessed from smaller radii, almost certainly.
So it's really only 15% increase, right?
No, that's because Assassin has a huge pixel. So if you look at, it's actually very luminous. It's actually a lot of brightness. It's actually extremely bright. This is 10 to the 50 ergs per flare. So it's quite bright.
Eliot, is it clear why this stuff should even accrete on the black hole? Okay, I have a star which is on some eccentric orbit. So you tidally perturb it so that it makes some material become unbound from it, but it doesn't mean that this material immediately joins the accretion disk if accretion disk is not there in the first place.
That's right.
How does it produce any
we know from people trying to calculate the circularization of the debris in TDEs that it's very non-trivial process. I think
They remain on near this eccentric orbit.
Yeah,
Okay, if there's some flying debris, it will stretch out in the same way as Eliot was showing when the star collides with a disk. Okay, so you make this kind of blob, and then this blob elongates along the orbit, and it doesn't, the blob by itself doesn't make a flare.
it definitely does not make
It
a,
only
either
collides with
the
this-
blob colliding with something or the blob accreting.
Yeah, the
makes
blob
the flare.
accretes.
I mean, I think the truth is that the circularization has not been thought about very carefully in this context. And it is as non-trivial a problem as the circularization. In the case of TDs, it is sort of the same problem.
But don't they do numerically these TDs?
They do, and yeah, that's like the whole, they don't get the right answer.
No, but
Oh, really?
sorry, but I think it's even harder here than in the conventional parabolic parabolic PD circularization, because here you really have this debris basically following the same orbit. With the parabolic stuff, you have
Right, so
you
there's
have-
an
you have-
interesting, there's an orbital period inside of which the tidal energy starts to become unimportant to the binding energy of the star. And that's like right around, it depends on the black hole mass, but it's actually around 100 days or 30 days. So you're absolutely right. So there's this interesting transition where if you have a period larger than, let's say, roughly 100 days, then it's sort of like the conventional TD picture where the initial binding energy of the star doesn't matter. If you're on a tighter orbit than that, then you're absolutely right. Then it does, you don't have half unbound debris, everything is bound. So
everything
that's a
sticks in
different-
the same orbit, right? If you're an orbit which is compact.
So we think
enough.
that 100 days
is right around, so you're
marginally-
right, this case is super complicated if this is actually tidally stripped material, because it's right at this transition. So I fully grant that.
So you don't really know what's happening here, right?
I definitely do not really know what is happening. I mean, I have some conjectures, but I think there.
Well, you think it is because of almost perfect periodicity modular PP dot. I understand it's a star, definitely.
I do, yeah. And so the other thing about this case, so there's a lot more data. This has X-rays. The X-rays aren't quite as nice timing wise, but that means I think it really is. You are forming. I would say you are forming an accretion disk that's producing sort of typical X-ray.
Every 114 days, you manage to form an accretion. That's very interesting.
It is very interesting.
But can it be like
that's
what
why-
you showed with ETI thing, that there is some small enough disk created by this tidal
By
disruptions, and then the
previous
material
stuff.
stays there, and every 114 days, when the star comes back at high eccentricity, hits this thing,
So-
and then it deposits this cloud not onto its orbit,
Onto
but
very
onto the disk which is already there.
So the only way we could come up with to explain this number was to have it be drag. So that kind of model is what we were forced to try to explain.
So did you come up with some kind of a hydrodynamic semi-model for this thing, or
I would say
is there a theoretical work explaining this thing? This is what I'm asking.
so it depends on which part. I think for this part, there's a theoretical work that pushes you into uncomfortably dense disks in order to have enough drag to create this larger.
So you wrote about this?
Yes.
Okay.
I would not say that that model is predictive of, the duration of the flares or.
But this
anything.
model doesn't contain eccentricity, for example,
It doesn't, well, that model does contain eccentricity.
but not in a measurable way, right?
Not-
It is high enough, basically.
Correct, yes, I would say you.
But there
you-
is actually a signal, if you do
Yeah,
believe the interpretation that this P dot is due to drag with a
Yes.
disk, then there is actually a way to measure the eccentricity,
Mhm.
which is the fact that when you have eccentricity, you also have apsidal precession
Mhm.
of the orbit, which means that the star will sample different parts of the disk.
And
as
then it
collides.
will not be strict periodicity.
right,
So this P dot will modulate, And
And you
if
can
the-
predict on which time scale, for
Yes.
example.
and then you could in principle.
And
yeah,
that would contain eccentricity.
Yes,
So if you keep monitoring it for 10
Right.
years, you will see some modulation of PP dot.
yes, so that was a prediction that we made.
So, and this is in your paper.
Yes,
So you did something on it, okay,
we
good.
did something.
So,
And these things are now monitored continuously?
Yeah, so every 114 days, I think there was now a phase where you couldn't observe it. It was maybe too close to the sun or.
anyway, I think I got off soon. I was gonna, yeah, so there's, you can, it's actually quite nice, you can predict P double dot, there should be all this interesting secular change in the time.
But of course with twiddles, right? Because God knows how the disk evolves, stuff like that.
So that's right. So I would say the way you have to make assumptions about, you can, okay, the thing you can obviously predict confidently is what the orbit is doing. How that translates into timing of flares, you have to make some assumptions about how the timing of the flare is associated with periastron passage, collision with the disk, right, etc.
And how, for example, do you orient your disk? Does the black hole spin enter? Stuff
Yes,
like
it does. So that's why it's so interesting, is that you should absolutely be able to see both nodal and apsidal precession.
You mean for this system?
No, I think actually the better systems, just so here nodal is hard just because time scale is going to be long. It's the shorter period ones that seem more promising for potentially detecting.
So one of these QPEs has a recurrence time of 2.5 hours.
Yeah,
Now
exactly.
we have a fairly long baseline.
Right.
So we're starting to look at trying to fit it to some orbital model. And it's unclear whether there's.
But even for this shorter time scale QPE,
Yes.
it's not excluded that the disk was created by the star itself. I understand according to you, TDE helps because it puts a disk there.
Yes.
But could it be self-created, like I think Eliot was
I
saying?
think especially for the shortest period ones.
It's very hard to put the star outside its own tidal radius. So to avoid Roshnov overflow, it's actually hard. So maybe that this.
So I think
is
that's
produced-
why
So you guys prefer pre-existing disks?
well, I would say in the shortest period cases, I think it is the most plausible that
Okay.
the star creating this. In the longer period ones, it's
Not
less
pre-existing, but self-generated.
self-generated.
No, self-generated for shorter periods.
Yes,
Yeah,
for
yeah.
sure.
Yeah, so this is good, right?
Yeah.
So although the system, how to say it, even though it starts as a simple binary, it very quickly becomes a funny binary because
That's
it
right.
surrounds itself with its own stuff.
That's right. And
Right.
probably the
And you need high.
disk
coordination.
probably aligns with the spin of the black
Something.
hole. The star's orbit is precessing relative. So you get precessing relative to that.
So that was collisions. right?
Yes, that is the thinking in the self-generated disk case, that initially, of course, the gas disk wants to be in the same plane as the star, but then the gas disk the inner part will align, and in any case, they'll differentially precess relative to each other. So the star will not be in the same plane as all the gas. So that will give you correct.
This is a nightmare.
And this gives you
It is. It's also a lot of fun.
Right, I agree.
It's a lot of
Have to
fun.
resist.
Hard
because
to
it is a
resist.
nightmare.
It is,
This-
yes.
this gives you the irregularity of the time.
That is the thought. That explains the regularity. And I would say there are attempts to turn that into a predictive model.
Mhm.
But they're very sensitive to what you assume the precession of the disk is. And is the disk undergoing Bardeen-Pedersen alignment? Is it precessing as a rigid body?
Mhm.
So the predictions that have been made assume the disk precesses as a rigid body. So you have a star on a precessing orbit, you have a disk undergoing rigid body precession, and you can calculate the timing of collision. So it's quite nice work trying to do that. And you can get a lot of stochastic timing variation that's not, that is, I would say, encouraging in light of what is observed. But I'm, the assumptions,
Also a lot of-
particularly about
a lot
what,
of knobs,
yeah, particularly about what the disk does, this rigid body precession, I think
The profile of the disk will be very important.
will be very important. Exactly. Where is most of the angular momentum? Right, exactly.
And what I think this meeting in Italy, somebody was showing profiles, which I thought were.
Yeah.
Right. That's the
I
group,
thought
right?
they were totally
Right.
nuts.
That's, I remember this conversation.
Right.
Yeah, that's exactly right. I think they had all of
All of the mass.
at small radii,
At
so
small
that you would
radii.
get very,
Yes.
very rapid disk
Yeah.
precession.
Yes.
Right.
And
Was
the
Because at least-
the justification was that radiation pressure wasn't contributing to, alpha was only. Sorry,
Yeah,
the viscous
like,
stress was proportional to the
yeah.
gas
Right.
pressure.
Beta
and also the
viscosity.
beta
Right.
viscosity.
But thank you, Eliot.
Yep.
I think now, so student of Erin actually doing some modeling, also accounting for pair
Mhm,
space-time, calculating the light travel time effect. So
mhm.
you do actually get weirder timing of the flares when you put all of that in. So it's not clear, and maybe you don't have to invoke really, crazy disk precession to
Mhm.
produce this feature phenomenology. But I would say, yeah, the weirder, there are some sources that seem to be more well behaved. But QPE1, for